At the core of radio, optics, and quantum engineering sits the resonant cavity. It is a bounded space designed to trap and sustain an oscillating wave. We measure the efficiency of these systems using the Q factor. This strict ratio divides the total energy stored within the cavity by the energy lost to the environment during each oscillation cycle. For decades, the standard engineering model has operated under a single assumption. To improve the Q factor, you can either inject more power through input matching, or you can manufacture smoother walls and better materials to minimize physical friction. This assumption forces engineers to view the cavity entirely as a passive storage container, engaged in a losing battle against thermodynamic decay. Under this closed system model, every resonator hits a strict mathematical ceiling known as the passive thermal limit. Eventually, the entropy always wins. Observer resonance theory predicts the existence of Super-Q systems. These are resonators with measured quality factors that surpass the passive thermal expectation by actively extracting structural order from environmental chaos. To understand how this works, we have to stop treating the cavity as a sealed, isolated loop. We have to analyze it as an open, interacting field system, deeply entangled with its environment. This requires an expanded thermodynamic equation that accounts for open system dynamics, tracking drive power, heat loss, and the raw ambient energy flowing across the boundary. The critical addition is this specific variable at the end, the phase geometry coherence term. This mathematical term demonstrates that under exact geometric conditions, a physical cavity stops acting like a passive bucket with a leak and begins operating as an open coherence engine. To maximize that phase geometry term, the cavity must function as a thermodynamic observer, a system capable of actively reducing its own internal entropy while exporting disorder outward. In nature, biological organisms act as permanent observers. They fight off thermodynamic decay and maintain low entropy states by utilizing highly durable chemical bonds. Cellular mitosis, continuous metabolic cycles, and protein folding are all examples of physical matter structurally binding together to enforce order over long periods of time. A Super-Q cavity completely lacks these biological mechanisms. It contains no self-repairing proteins and no permanent chemical bonds. Instead, it acts as a temporary observer. It achieves a low entropy state by borrowing its internal coherence entirely from a driven, transient field configuration. This shifts the definition of observation away from strictly biological permanence, extending it to engineered systems sustained by transient haze alignments. This raises a severe mechanical problem. How does a transient, unbonded system force ambient entropy uphill to create a highly structured internal state? This diagram shows a standard thermodynamic dipole. When a hot energy source is connected directly to a cold sink, the energy flows downward and scatters evenly. It thermalizes, producing zero internal organization. To generate structure, observer resonance theory relies on the Tripole Entropic Mediation Architecture. This inserts a third, symmetry-breaking element directly between the source and the sink. This mediator acts as a highly selective directional valve. It accepts and synchronizes specific frequencies of entropy while actively rejecting and scattering non-resonant thermal noise. In a physical Super-Q resonator, the physical boundary geometry of the cavity serves as this mediator. Without a precisely engineered geometric boundary acting as an asymmetric valve, coherent energy accumulation remains physically impossible. This leaves the defining engineering question: exactly what physical shape must this boundary take to lock the phase of ambient entropy? Standard engineering frequently designs cavity dimensions using simple composite mathematical ratios, like 1:2 or 2:4. This spectral frequency chart maps a 1:2 composite dimensional ratio. Notice how the scaling frequencies naturally generate dense clusters and heavily overlapping harmonic nodes. In acoustics and electromagnetics, this phenomenon is called degenerate mode clustering. When frequencies overlap at these nodes, the energy inside the cavity chaotically scatters between them, creating destructive wave collisions. This violent internal scattering shatters the delicate phase locking necessary for the system to function as a temporary observer. The required solution is prime modal geometry. This dictates that cavity dimensions must be built entirely on prime numbers, utilizing ratios like 3:5 or 7:11. Because prime numbers are only divisible by themselves and 1, they create mathematically irreducible fractions. Applying a 3:5 prime ratio to our chart produces a sparse spectral landscape with strictly isolated frequencies. Without exact mathematical coincidences, the energy is trapped in its specific mode. It physically cannot scatter into chaotic adjacent channels. This isolation guarantees the clean, uncorrupted fundamental oscillations required to pull order from the environment. Utilizing prime geometries is a strict physical requirement. It starves the cavity of chaotic scattering, establishing the exact conditions needed to lock in Super-Q coherence. When we combine the open thermodynamic system, the tripole architecture, and prime modal geometry, we get the complete Super-Q operating cycle. This cyclical flow diagram shows the process in motion. A chaotic field of ambient entropy continuously strikes the precisely engineered phase-locked boundary. The prime geometry of the boundary filters this noise, funneling the viable entropy inward to generate a highly stable, coherent internal storage mode. To complete the cycle, the system transduces this coherence into useful output, while the residual waste entropy is safely exported back out into the environment. This cyclical flow of entropy reduction perfectly mirrors the thermodynamic loop of a living biological observer, executed entirely through mechanical geometry. Operating this cycle leads to the most controversial outcome of the Super-Q framework, a system capable of achieving a coefficient of performance, or COP, greater than unity. In classical physics, producing more coherent output than the power you put in appears to be a blatant violation of the first law of thermodynamics. This paradox is caused by a measurement error. Standard efficiency analysis only measures a drive-referenced COP, drawing a restrictive box that only counts the direct power cord plugged into the wall and the final output. When we shift to open system thermodynamics, we have to expand the accounting boundary. We must include the massive ambient reservoirs the system is actually interacting with, the thermal background, the acoustic medium, and the surrounding vacuum modes. When recalculated across this fully expanded boundary, the total system COP remains strictly at or below 1. The laws of thermodynamics are perfectly preserved. Engineering is shifting away from building passive boxes designed simply to hold on to energy. The focus is now on constructing precise boundaries capable of actively mining structural order directly from the universe's thermodynamic noise.